So, what if I told you that one of the biggest problems Albert Einstein ever faced wasn't solved by him, but by a little-known mathematician who completely turned physics on its head? It's an incredible story about a cosmic puzzle, a forgotten genius, and maybe one of the most beautiful ideas in all of science.
Let's start with a little thought experiment. Picture this. You're out in the total emptiness of deep space. You throw a rock. Basic physics, right? Newton's laws tell us that rocks should just keep going, forever. But what if, after a few million years, it just stopped? That feels wrong, doesn't it? It completely breaks one of the most sacred rules in the book, the conservation of energy. Energy can't just vanish. So, where did it go? The answer is going to change the way you think about the universe.
All right, to get to the bottom of this, we have to go back in time, way back, to 1915, where Albert Einstein himself was staring down a massive challenge with his brand new theory. This is where it all begins, with a cosmic paradox. Einstein had just dropped a bombshell on the world, his theory of general relativity. It was absolutely brilliant, a whole new way of looking at gravity. But there was this huge, glaring hole in it. The math just didn't add up. In the strange curved spacetime that Einstein described, it looked like energy wasn't conserved. And for a law that was, the bedrock of all physics, this was a really, really big deal.
And it wasn't just Einstein scratching his head. Over in Göttingen, Germany, the legendary mathematician David Hilbert took a shot at it too. And he actually found a sort of solution, but it had a massive catch. It only worked in a universe with absolutely nothing in it, which, is pretty useless for describing our universe, which is full of stuff. The greatest minds on the planet were completely stuck.
So Hilbert did something smart. He turned to a colleague for help, someone he knew saw the universe in a totally different way. She was a quiet, unassuming mathematician, but she was an absolute master in one particular area. She was the symmetry expert. Her name was Emmy Noether, and she was about to change physics forever.
Emmy Noether was, simply put, a force of nature. This was a time when women weren't even officially allowed to be students at universities, but that didn't stop her. She just sat in on classes unofficially and became one of the world's leading experts in an area of math that, it turns out, was the key to unlocking the whole mess: symmetry.
So what is symmetry, really? It's one of those ideas that's super simple on the surface, but incredibly deep. Basically, a symmetry is just any action you can perform on something that leaves it looking exactly the same as when you started. For example, think about a perfect equilateral triangle. You can flip it over along its 3 different axes, or you could rotate it by 120 degrees, or 240, or a full 360. After you do any of those 6 specific things, it looks completely identical to how it started. Those are the symmetries of a triangle. Now that triangle has a set number of symmetries, right? 6 of them. We call that discrete symmetry. But Noether was the master of something even more powerful: continuous symmetry. That's when there are an infinite number of actions that leave something unchanged. Think of a perfect, infinitely long line. You can slide it any amount you want, a millimeter, a mile, half an inch, and it still looks exactly the same. It's that kind of infinite continuous symmetry that, it turns out, secretly runs the entire universe.
And this right here is where it all comes together. Noether's great insight, her stroke of pure genius, was connecting that abstract idea of continuous symmetry directly to the hard, concrete laws of physics. And in doing that, she was about to solve Einstein's problem for good.
This is it. This is the big one. Now, it's called Noether's first theorem, and it is just so profound. She proved with pure, undeniable mathematics that conservation laws, like the conservation of energy, aren't just some random rules that we happen to see in nature. No. They are a direct result, a necessary consequence of the symmetries of our universe. Her theorem is like a beautiful Rosetta Stone for physics. It shows that if the laws of physics work the same way everywhere you go in space, that's a symmetry, then momentum has to be conserved. If the laws are the same no matter which direction you're facing, another symmetry, then angular momentum is conserved. And here is the absolute kicker. If the laws of physics don't change from one moment to the next, if there's symmetry in time, then energy must be conserved. Okay, so without diving into pages of equations, the logic is just beautiful. Noether started with a simple assumption. Let's say an experiment gives you the same result today as it does a second later. That's time symmetry. She then showed the symmetry forces a special mathematical thing called the Lagrangian to act in a very specific way. And using the tools of calculus, she proved that because the Lagrangian acts that way, another quantity is mathematically forced to stay constant, forever. And what was that constant quantity? You guessed it, the total energy. It was an absolutely bulletproof proof.
So now, finally, we can go back to our mystery from the beginning, the leaky universe. Remember our rock in deep space? Well, Noether's theorem just gave us the perfect tool to figure out exactly what happened to its energy.
Everything hinges on this. According to Noether's theorem, energy is only conserved if the universe has time symmetry. So that leads us to a really simple but incredibly deep question. Are the laws that govern our universe actually the same, moment to moment, over the vast expanse of time?
And the answer, which is pretty shocking, is no, not on the grandest scale. We know for a fact that the universe is expanding. And not only that, the expansion is speeding up. That means the universe of billions of years ago was a much different place, denser, hotter, and the universe of the future will be different still. On a cosmic scale, our universe is not symmetric in time.
So you might be thinking, wait, then why does energy conservation work so perfectly in all my physics classes? Well, it's about scale. Over human timescales, days, years, even centuries, the expansion of the universe is so incredibly tiny that you can just ignore it. So for all practical purposes, time symmetry holds up and energy is conserved. But when you zoom out and look at the universe over billions of years, that expansion becomes a huge deal. The symmetry breaks and global energy conservation goes right out the window.
And that brings us back to our lonely rock. As it flies through space for eons, the very fabric of the universe it's traveling through is stretching. And because of that stretching, the condition for energy conservation, time symmetry, isn't met. So the rock's energy just fades away. It doesn't turn into heat or light. It doesn't go anywhere. It just ceases to exist. Mind-blowing, right?
Now, this idea of local versus global conservation is really key, and another of Noether's insights helps us understand it. Here's a good analogy. Think of energy as water flowing through the pipes of space-time. In your little local neighborhood, say our solar system, the pipe is perfectly sealed. Water in equals water out. Energy is conserved locally. But Einstein's theory says that space-time is curved, and that curvature creates tiny, tiny cracks between those local sections of pipe. So on a huge cosmic scale, energy can actually leak out. It's conserved here, but not everywhere.
And here's the thing. Noether's work didn't just clean up Einstein's mess. Her insight was so profound that it became a foundational pillar for pretty much all of modern physics. She gave us a new language to describe the universe.
But despite her absolute genius, Noether's life was never easy. After years of working for free, she was finally given a paid position, only to have it stripped away by the Nazis because she was Jewish. But even then, she didn't stop. She literally taught math classes from her own kitchen, even, unbelievably, to a student who showed up in a stormtrooper uniform before she managed to escape to the US.
And the man whose theory she had saved never forgot it. After her death, Albert Einstein himself wrote this incredible tribute. He called her the most significant creative mathematical genius thus far produced since the higher education of women began. Coming from Einstein, that's just wow. Her legacy today is just immense. This idea that symmetries dictate the laws of physics is the guiding principle for everything we know about particle physics. It's how we figured out the fundamental forces of nature, it's how we predicted the existence of quarks, and even how we found the Higgs boson. Her work isn't just a part of modern physics, it's the very language it's written in.
Which leaves us with one last incredible thought. Emmy Noether taught us that underneath all the chaos and complexity of the universe, there are these simple, beautiful, elegant symmetries pulling the strings. So you have to wonder, what other deep, fundamental truths about reality are still out there, just waiting for us to find them, hidden in the simple language of symmetry?